So this is what we have been discussing. The wire wound one, linear and angular, the conductive plastic one.
Yes.
And we were not happy with this, right?
Which is why we came with the conductive plastic.
Yesterday I was trying to draw a figure of this in the linear fashion. I have a picture now here.
It's much bigger.
Much.
Yes. Roll it up. Roll it out.
Yes. So, I mean, this is a one for angular measurement.
Yes.
Now, if I want X, the linear displacement, this is what I could use. So, if you look at this figure, I mean, I can see one contact here. The other contact is available here, which is actually brought to this point in the PCB.
Right.
So, just for convenience, I can, the excitation is given across this. Sorry, whatever 10 volt that we marked yesterday.
Yes.
Or BS is given across this. No, so now you see the wiper.
Yeah.
Which I was struggling to draw yesterday. I mean, this is taken outside and rotated 90 degree here in the photograph.
Right.
So, but the point is, you see the structures that will be on these traces, right? And I rotate and keep it here. So when I move, basically these points will be moving. Or suppose if I keep here, there will be a contact like this. So whatever voltage I have at this point will be available here. And that I will watch from here, right? Using a meter or using a system to record.
Fraction of the full voltage.
Yes. So as we discussed yesterday, when you are here, it's a 0 voltage. And when you are at the center, you have Vs by 2. When you're here,
full scale.
Yeah. And if you want, let's say, 0 here and plus or minus X, like we have seen in the case of joystick, we can apply
-5
plus voltage and minus voltage at both sides and then get 0 at the center. And then
if we want the exact position.
Yes. Exact position in terms of positive and negative.
Positive and negative, yes.
Yeah.
If you have a quadrant, for example.
Yeah. In many applications, it may not be required.
Yeah.
But if it is required.
Yeah.
Now, see, whatever we do, suppose if this contact is not maintained, if I don't touch, I don't get the same voltage at the other side.
No.
Yeah. So that's a critical component. So what we are saying is, you move like this and you get the output, you are happy. But what happens if this contact is not there?
You mean one side?
Let's say it's lifted up like this. Both
contacts.
Yeah, both or one, doesn't matter. If one is open, then it's
right.
Yeah, in this case, let's say both are lifted up. I still move, but there will be no output.
But if it's lifted up, right? So you have a conductor below and a conductor top. Then then you're basically now saying.
So what you're saying is this wiper is some conductive surface. And then this resistive sensor below.
Yeah.
So here the figure is anyway planar plane.
Right.
So there are two conductive surfaces.
So then?
And it is separated by some air gap.
Yes. That sounds like a capacitor.
Or is it?
Paraplate or capacitor?
So what you're saying is you have two electrodes like this. One is this, the other one is this.
Yes.
And then you have two contacts.
Correct.
Oh. So the RAB here is like a resistive element like this.
Yes.
And wherever the wiper is, I mean, let's say we mark this point as some O or something. So this O is here. From there to here, there is a capacitive coupling.
Could be. Because you said maybe we'll not get anything if we lift it up. But maybe because there's some capacitive coupling, maybe there'll be some output.
There is some capacitance.
I don't know, but this is what I'm thinking.
Yeah, you are right. Definitely there is some capacitance. But one thing, so far we were using excitation like this DC. So if I put a meter here, this voltmeter I have been drawing so far.
Yes.
I don't know whether I will get something.
That's true. I think, this is what I think. Because in the previous lecture, we talked a lot about contact, right? Now you're talking about no contact. Now, even if you do get something, I'm thinking maybe it will be very small. But that's a problem, right?
Yeah.
Because then how are you going to measure this?
Correct. I don't know whether our students have used this kind of voltmeter.
Right.
So any voltmeter we take, that will have some input resistance.
Right.
So I can replace this with a large resistance. Let's say R is the meter resistance.
Yes.
And let's say I have some X volt here. I gave this Vs. So depending on the position of X, there will be an X volt there.
Correct.
It's a DC voltage. So this capacitor is now connected to ground through this resistor.
Right.
So basically it will charge to this X volt.
Yes.
And then finally the voltmeter reading will be 0. Correct.
Yes.
Yeah.
Capacity charges.
Yeah. So that means if I give a DC excitation like this, it may be hard to use this guy.
Yes. Correct.
We may have to use some AC excitation.
Yes. I think in your back end now, your readout electronics is maybe a little more complex now.
Yeah.
Compared to what
I cannot directly
just put a voltmeter and measure.
So what you're saying is if you can do something there,
yes,
probably we can still measure.
Maybe.
If I do that, will there be some benefit? Okay. What you're saying is, okay, when it is lifted up, there is some capacitance formed. Why don't you make use of that? But if I do that, what is the benefit?
I think the biggest benefit is because, again, the last lecture we talked about contact and all the problems we had with contacts, right?
Correct.
Now we're not touching it.
We're not
touching.
If we can do that, then we are not bothered about this connection.
We don't care.
That physical connection, which introduces friction and all kinds of. It was a critical connection.
Yes. And we saw the troubles we had, right? But also the capacitance, because now you pulled it up, right? That height might also add some complexity.
Correct.
Right? So somehow...
So the value of that capacitance may be very small.
Yes.
And as I move, it may also vary. Correct.
So somehow we had to take capacitance out of the...
Final
output. Because
what you're saying is the final output should not depend on the value of the...
No.
So if this capacitance is Cc, I should get a reading independent of the value of the Cc.
Yes, we cannot depend on the capacitance for the final output. That should still depend on your resistance. This is what I think.
Okay. So that's why you said the electronics or the measurement circuit may become a little bit complicated.
Correct. Now our sensor, maybe the design is better in the sense that we don't have to worry about this contact. But then it adds some complexity.
It will become more reliable.
Yes.
Correct? Because
it will become more reliable. You're correct.
Yeah.
But then we have to worry about the consequences in the readout electronics.
Correct. Oh, you have made my life more complicated. So this is what you are saying. If we represent that something like this, then you will have to have something more at the measurement side.
Yes.
To get the exact value of X.
Exactly. Right.
So this means we may have to work a little bit hard. Or some better way of representing and so on.
Yes.
Or a different way of representing and so on. So this resistive element, let's say these terminals are P1 and P2. Okay. So far I was using A, B. We now changed to P1 and P2 just for convenience. So the same P1 and P2, the resistive element, I have kept here. Now let's say this is the point at which the wiper is present. So between the wiper and the resistive element, there is some capacitance Cc which is formed. Yes. And the total resistance between P1 and P2, let's say that is RT. Okay. This to this. Now, from P1 to the wiper position, we are marking it as R1. And again, from P2 to the wiper position, we are representing it as R2. Yes. And of course, what we are measuring is X, the quantity X. Yeah. Oh. Also, X. Let's say yesterday we were talking about range. Now, let this be marked as, if the wiper is here, I will say X is -1. Okay. And if the wiper is here, I will say X is 1. Okay. So if at the center I have 0, X is 0. It is similar to our joystick that we mentioned. Right. So it can be at 0, go up to -1, go up to +1.
Based on that, we know exactly.
Yes. So total resistance is R1. Sorry, RT. This is R1. This is R2.
And in this position, it's R1 plus R2.
Correct. Yeah. And finally, what I want to measure is X. Yes. So can we somehow represent this R1 in terms of X and maybe RT, because RT is fixed anyway.
Yeah, RT is fixed.
We can try maybe. Let's try. So I want definitely X.
Yes.
RT also we know. Let's keep that. RT into X. Is there a possibility? No. Or let's see. If the wiper is here, R1 is 0. Yes. But X will be 1 at that time. Correct. So R1 will be RT. Is wrong. So maybe RT into 1 minus X or plus X. Which one you want to try first?
Let's try plus first.
Plus X. Will this work?
Move it up.
So if I'm here,
X is 0.
X is 1. X is 1.
Yeah.
So 2 are wrong.
That's wrong.
Also. So that means minus may work. 1 minus 1, 0. Okay, that is working. Yes. What about if the wiper is here? R1 has to be RT. Yes. So if the wiper is here, X is -1. So 1 minus -1, 2 RT, which is not correct.
Then?
So I had to put maybe RT by 2. So this is R1. The students can try out and find out whether it is right.
They can just plug in values and see.
Yeah. So if R1 is this, R2 will be just opposite of that.
Yeah.
So this will be RT by 2 into 1 plus X. Because when one increases, the other decreases. That is how it is. Correct. So what we have is 2 resistors, R1 and R2, that change with respect to X, the measurement X. One increases, the other decreases. Correct. So if this is plus, this is minus. Sorry. If this is minus, this is plus, and vice versa. Okay. This is only some representing in terms of
still need to find
I need the X. And you were so insisting that it should be independent of CC.
It's
final output should not be. Yeah. What they will do. And we were saying DC excitation is not going to help.
No.
So it's just AC excitation. Let's try. So what is this? So let's say US, this is the excitation, sinusoidal excitation. This is the P1, P2 element. Okay. And the coupling capacitor CC is here.
Yes.
Let's say I connected this to ground and then I am measuring this current. Okay. We are just trying to figure out whether something will work or not. Yeah. So if it is like this, what will be this current? It's not straightforward. Yeah. Maybe I have to use something what we have learned in the previous course. Maybe I will take this as a load. From here to here, I will consider as a load. Okay. And I will Thevenize this circuit, keeping this as the output point. Okay. So that means I will open circuit here and look what is the voltage here. That will be voltage across R2. So that's, I will use same Vs maybe. Vs into R2 by R1 plus R2. That will be the Thevenin VTH, Thevenin equivalent voltage. Now, Thevenin equivalent resistance, I am going to look from here and the source will be short circuited. So, what we see here is R1 and R2 are in parallel. Yes. When I look from here. So, that means RTH is R1, R2 by R1 plus R2. Okay. Yeah. So this means I have a Thevenin equivalent voltage, a Thevenin equivalent resistance. And then I just have to connect CC here and calculate what's the current going through this. Yes. Which is straightforward. Yeah. So the I1 will be the voltage Vs into R2 by R1 plus R2 divided by the total impedance, which is R2 by, R1 R2 by R1 plus R2 plus 1 by J omega CC. Okay. So what?
So we have something now.
Yeah, if I measure this current, you will hit me because there is a there is CC percent.
Exactly. So that's still a problem. How do we get rid of that?
So
we want to get rid of that, but also have, yeah, that's right.
Yeah. What will maybe we'll flip this and measure and see what happens.
Well, if you're going to flip that, why don't you flip the...
Because when I flip also, when I say flip, I'm going to flip the excitation to P1 and P.
Okay.
So I'll change these two excitation I will change.
Right.
Which means the Thevenin equivalent resistance will remain same.
Yes.
This will also be same.
Yes.
And suppose if I measure the current there, denominator will be same.
So it will cancel.
There is a possibility. Numerator will be different.
Yes.
We'll try that.
Okay.
So basically, the same excitation Vs.
But now you
flip it. We are giving it to, P1 and P2 we interchanged. Yes. Now P1 is at a negative voltage. It's positive. P2 is a positive. Again, we will apply open circuit this. See the VTH here. VTH now is Vs into, because this is at ground now. So I will have to look at this voltage. Yes. Which is R1 by R1 plus R2. Correct. RTH will not change. Because I am looking from here, and then this is short circuited. It's R1 parallel R2.
Yeah.
Everything else is same. So I2 will be Bs into R1 by R1 plus R2
divided by
the same thing.
R2.
R1 R2 by R1 plus R2 plus 1 by J omega Cc. Again, your Cc is there.
But then now we can...
seems there is a... Suppose if we take a ratio or something. Something, at least the denominators will get cancelled.
Yes.
We will get maybe R1 by R2 or R2 by R1. Correct?
This is what we need.
Yeah, from there...
Something without the capacitance.
Yeah, from there we may be able to get the X. So we have these two currents. I think we got the expressions correct. Now, we were talking about the ratio. You were saying that, maybe we can, suppose if we take a ratio, finally it will become, suppose if I do the ratio, these two will get cancelled.
Correct? If you take the ratio, yes.
Yeah. So this will go, this will go. These will also go. US, of course, anyway, it will go. Finally, it is R2 by R1.
Now we have X.
Yeah. So
X just appeared.
Yeah. So this is the expression we had for R2.
R2.
And this is for R1.
So from that.
When you do ratio here, these are also gone.
Yes.
So I have 1 plus X by 1 minus X.
Very elegant. Very nice.
Yeah. So from here, I can rewrite for X is equal to.
Yeah.
Correct. Right? So that I have done. X is R2 minus R1 by R1 plus R2.
It's plus or minus X.
Yeah.
With the,
correct. But now, where we started is the ratio between these two.
Yes.
But now we realize, to get an X, it's better if we have R2 minus R1 by R1 plus R2.
Yes.
How can I get that from this? We can just do, maybe I can see R2 here. So the R2 is here. R1 is there. R1 is there. So that means I1 minus I2. If you do, the whole thing will be there, but the R2 minus R1 will also be there, right? Then we divide by I1 plus I2. Correct, no? So all these denominators will get cancelled, and finally you will get R2 minus R1 by. Yeah. So what we finally see is, if you measure, you excite that P1 and P2 with one source, measure the current going through the CC.
Yes.
Then you flip the excitation, measure the current once again, do this operation. It's called as ratiometric operation.
Ratio what?
Ratiometric.
Ratiometric. Okay.
You are doing a ratio of, difference by sum. Right? That actually gives us this.
Which in terms
actually gives this. So now we are happy.
But then, that means you have to switch the power supply very fast.
Yeah. So the excitation to this, I can switch. Let's say you want to measure at 10 hertz.
Yeah.
Every 10.
At going like this.
10 hertz. Yeah. I will maybe switch at 100 hertz or 1000 hertz because it's only electronic switching.
Exactly.
It's not manual switching.
So it has to be much faster than
the speed at which
the
you want to measure.
The white is moving. Yeah.
Correct. Yeah. And now you must be happy because this doesn't have any CC component there.
There's no capacity.
CC starts seen.
So that does not influence the final value.
Or the absolute value of CC.
Yes.
Is not there as the output.
Yeah.
So
So that's also a nice way then.
Yeah.
Of
so what you said seems to be possible. You can still, have the wiper, but lift it a little bit. Maybe you don't need wiper with those fingers anymore. It can be just a flat wiper.
Yeah.
And to keep a small distance, small gap. And you don't bother about that gap at all. No sense variation in that gap.
And no friction.
No friction. So all problems are solved. Only thing is, to realize what we said now, there will be some amount of electronics that is required.
Yes.
That I think for now we will leave it. Later, if time permits, we will see how to realize this using electronics. Otherwise, one could measure, digitize these two and then do it in a microcontroller or a processor and get the output. Using an ADC and then a processor. That's also possible.
Yeah.
But the logic is this.
Yes. Very nice. Another different way, right?
Yes. So we started with very conventional potentiometer, which was 1873 or something. First patent. 1871. Yeah. Still in use. We have seen the conductive plastic one, which is smooth, which can be produced, mass manufactured.
Yeah.
Still, there is a contact requirement. Wiper has to be in contact properly.
Yes.
Now we see a slightly advanced version where all those technical problems we face there is solved.
By electronics, by the back end.
Exactly. Yeah. So this electronic system plays a role.
Yeah. So that means, Boby, it's not just the sensor.
Yeah.
The electronics also, even important component of the whole system.
Yeah. Yes. Yeah. So the combination makes sweet.
Exactly.
Right? Yeah.
What would you prefer though? If you were, asked to design something, would you focus on the sensor or would you focus on electronics?
I would love, I love both. So we'll try to find the, very
middle ground.
Yeah.